In Course 3, we showed you how to use reinforcement learning with function approximation. We covered how to approximate value functions and policies using neural networks and fixed basis approaches like tile coding. We discussed how function approximation allows for generalization, which helps the agent learn faster.
But we might lose some of the ability to discriminate between the values of states. The function approximator may no longer be able to get all the values right.
The agent then has to decide how to balance accuracy across states, how to allocate its limited approximation resources. We introduce objective functions to specify how to balance approximation error, and discuss gradient-based algorithms to optimize those objectives.
Using all this new knowledge, you are ready to implement a complete reinforcement learning system. You will study a problem that highlights some of the challenges you might face when applying RL in the wild.
In Course 4, you will be putting together your knowledge from Courses 1, 2, and 3 to land a lunar module on the moon. When Adam and I start working on a new problem, we start by having meetings to brainstorm about how to best frame the problem and gather ideas about potential solutions. There's rarely one right solution. Throughout, we will reason with you how we might approach designing an agent for this problem.
We will start by discussing how to formalize the problem as an MVP. If someone just told you, design an agent to land this lunar module, you would have to figure out how to turn that goal into a problem formulation. So that, of course, is where we begin.
Then we'll think about how to choose an appropriate learning algorithm. An important part of this is actually thinking about all the details of the algorithms involved. This includes determining how the agent explores, the type of function approximation architecture, details inside the function approximator such as the number of features it produces, and the list goes on.
A big part of this course is understanding the importance of all these details and how to try to gain some insight into how your algorithm behaves with different choices. Practical implementation begins with understanding.
So, let's not just sit here talking about it, let's dive right in and get our hands dirty.
With moon dirt, of course.
Hi, I'm Martha. I'm an assistant professor at the University of Alberta.
Hi, I'm Adam. I'm a research professor at the University of Alberta and a senior researcher at DeepMind.
Adam is well known for his work on predictive knowledge for reinforcement learning. Several research groups around the world are building on these ideas. I personally think it is some of the most important work in recent years and will only become more influential. He's also an impressive empiricist, a real master of designing experiments to cut to the key issues. He's constantly trying to improve scientific understanding in the RL community.
Martha's algorithmic contributions to reinforcement learning are too many to list here. She has developed several new off-policy learning algorithms, new approaches to policy gradient, and dozens of impressive contributions to representation learning. She is truly one of the young rising stars in reinforcement learning. She also happens to be my most frequent co-author and my partner in life.
So how did you get into computer science?
Well, I grew up on the East Coast. In high school, I was really interested in the sciences, physics, chemistry, biology, but I couldn't really find a right fit. And so I kind of randomly took a course on computer science and programming, actually, in GW Basic. And it was really just a career-defining moment for me because I just remember the first time, implementing an if statement or a for loop, and it was just amazing to me that I could get a computer to execute a sequence of instructions for me. And so from there, there was no hope. I was always going to do computer science in college.
Okay, and then from there, why did you start working on reinforcement learning?
So for graduate studies, I moved out to Alberta, and I came out here to do parallel distributed computing. That's what I kind of focused on in my undergrad. So I had all my courses loaded up with, systems courses, and I had one more elective to fill. And so I was looking around for a course to take, and I did a very reasonable strategy. I looked at the pictures of the professors, and I picked the friendliest looking professor I could find. And yeah, that turned out to be Rich Sutton, and it was Introduction to Reinforcement Learning. And that course was amazing. It was really inspiring. It was my first introduction to artificial intelligence or machine learning of any kind. And so I remember one of the early assignments in that course, we were implementing SARSA to do a grid world. And again, it was another career-defining moment for me, just watching this agent learn to solve this maze. And all it got was this reward signal, -1 per step. And somehow it figured out this amazingly efficient path out of the maze. And again, it just amazed me, and I was hooked, and I was going to keep doing that for the rest of my life. So Martha, how did you end up doing research in machine learning and artificial intelligence?
Well, I actually started my undergrad in math. I've always thought functions and dynamical systems are beautiful. And then I just took a CS course for fun, and it really was very fun. So I just continued in both math and CS. And those two topics go really well together for AI and machine learning, actually. So and then I did some research in AI in the summertime and just continued from there. And I really just stayed in the field because over time I realized it was more than just about functions and math. It's really a community where you get to collaborate a lot and you get to make a career where you help people. So my day, I get to mentor a lot and I get to work in a big team working on hard problems, and it's really just very amazing to get to work on such interesting questions in a team. So there's probably some people who are taking this RL course because they want to do graduate studies in RL. So what's one of the most important things you learned in your graduate studies?
Well, maybe surprisingly enough, I learned a lesson that's useful across probably all the sciences and in fact just any form of research. And that's to really love coming to understand the details of things, to focus and do small problems and understand them really, really well. And that's something that I think is really applicable across a wide range of things, and it's something that I pass on to my students in my classes, and I really focus on teaching my graduate students that, and it's something that I hope to share to the people taking this specialization.
So what do you like about your job?
Well, I love doing research, but sometimes that can kind of grind you down a little bit. Like it's really long hours, the peer review process can be a little frustrating. And so in those times when you kind of step back and look at your research, it can seem kind of small and a little bit insignificant, and it's hard to see where that's going, how that's going to impact the world and make it a better place. And so in those times, you can always fall back and think about teaching and mentorship, right? Teaching is where you get to help people learn about things for the first time, to come to understand how your field works, and it's just so exciting. And you're also being part of the beginning of their careers, whether they end up in academia or industry or starting their own companies. It's just such an amazing experience to be part of that process. And throughout my week, the best day for me is always the days when my schedule is full of meetings with my students and I get to help them work on their problems and come to understand reinforcement learning better. So why do you think it's so important to work on reinforcement learning?
Well, I think the promise of RL is really big, but there are still a lot of open challenges. Machine learning has started being used much more widely, but RL has kind of only been used in a few areas. But at the same time, I think RL can have a really big impact. And I think within the next decade or so, we're going to see more control engineers actually using RL in their systems. We're really just going to see that it's a tool that can help in automated decision making, really within larger engineered systems. But I think for that to really happen, we need to make some advances in RL. We need to start thinking more about how we're going to have robust algorithms and how we're going to get people to be comfortable using these algorithms. So I think alongside adoption in industry, we're going to need to be thinking about how we can improve RL algorithms so that these two things can happen together. So how about you? Why do you think RL is good to work on?
Well, naturally, I think reinforced learning is just the exact right framework to study AI and to make progress towards solving AI. But RL is also really important to me because I'm very interested in developmental learning systems. So you can think about, humans, babies playing on the floor or young animals learning about the world. I want to learn about those systems and how they work. And if you think about those systems, they learn an enormous amount in such a tiny amount of time. Right? They learn how to crawl, they learn how their bodies work, they learn how to interact with their environment, manipulate objects, communicate with other agents in the world, and they're very competent learning systems, and they do that over like a couple weeks to a couple months, and it's just really astounding. And it feels like we have so much work to do to get close to those kind of systems. And so I really want to come to understand the algorithms and the representations that those systems might be using. And I think reinforcement learning is the right lens to look at those things and to come to understand those things. So applications always kind of drive interest and excitement in the field, and we've had a few of them in games and some industrial control problems. But what do you think is going to be the next big thing in reinforcement learning?
Well, at its heart, I think RL is just a general approach to automated decision making. It's a tool that's going to help us in a lot of our engineered systems. And so I think the place we're really going to see it take off is in industrial control. In industrial control, we have experts that are really looking for ways to improve how well their systems work. And so we're going to see it do things like reduce energy costs or save on other types of costs that we have in these industrial control systems. And in the hands of experts, we can really make these algorithms work well in the near future. So I really see it as a tool that's going to facilitate experts in their work rather than, say, doing something like replacing people or automating them away. The K-arm bandit problem we looked at previously introduces many interesting questions. However, it doesn't include many aspects of real-world problems. The agent is presented with the same situation at each time, and the same action is always optimal. In many problems, different situations call for different responses. The actions we choose now affect the amount of reward we can get into the future. The Markov decision process formalism captures these two aspects of real-world problems. By the end of this video, you'll be able to understand Markov decision processes, or MDPs, and describe how the dynamics of an MDP are defined. Let's start with a simple example to highlight how bandits and MDPs differ. Imagine a rabbit is wandering around in a field, looking for food, and finds itself in a situation where there is a carrot to its right and broccoli on its left. Our rabbit prefers carrots, so eating the carrot generates a reward of plus 10. Eating the broccoli, on the other hand, generates a reward of only plus 3. But what if later the rabbit finds itself in another situation where there is broccoli on the right and carrot on the left? Here the rabbit would clearly prefer to go left instead of right. The K-arm bandit problem does not account for the fact that different situations call for different actions. It's also limited in another way. Let's say we do account for different actions in different situations. Here it looks like the rabbit would like to go right to get the carrot. However, going right will also impact the next situation the rabbit sees. Let's say just to the right of the carrot, there is a tiger. If the rabbit moves right, it gets to eat the carrot. But afterwards, it may not be fast enough to escape the tiger. If we account for the long-term impact of our actions, the rabbit should go left and settle for broccoli to give itself a better chance to escape. A bandit rabbit would only be concerned about immediate reward, and so would go for the carrot. But a better decision can be made by considering the long-term impact of our decisions. Now let's look at how the situation changes as the rabbit takes actions. We will call these situations states. In each state, the rabbit selects an action. For instance, the rabbit can choose to move right. Based on this action, the world changes into a new state and produces a reward. In this case, the rabbit eats the carrot and receives a reward of plus 10. However, the rabbit is now next to the tiger. Let's say the rabbit chooses the left action. The world changes into a new state where the tiger eats the rabbit and the rabbit receives a reward of minus 100. From the original state, the rabbit could alternatively choose to move left. Then the world transitions into a new state and the rabbit receives a reward of plus 3. The diagram now shows two potential sequences of states. The sequence that happens depends on the actions that the rabbit takes. We can formalize this interaction with a general framework. In this framework, the agent and environment interact at discrete time steps. At each time, the agent receives a state ST from the environment from a set of possible states, script S. The configuration shown on the slide is an example of a state. Based on this state, the agent selects an action AT from a set of possible actions. Script A of ST is the set of valid actions in state ST. Moving right is an example of an action. One time step later, based in part on the agent's action, the agent finds itself in a new state ST plus 1. For example, this state where the rabbit is next to the tiger. The environment also provides a scalar reward, RT plus 1, drawn from a set of possible rewards, script R. In this case, the reward is plus 10 for eating the carrot. This diagram summarizes the agent-environment interaction in the MDP framework. The agent-environment interaction generates a trajectory of experience consisting of states, actions, and rewards. Actions influence immediate rewards as well as future states, and through those, future rewards. So how can we represent the dynamics of this interaction? As in bandits, the outcomes are stochastic, and so we use the language of probabilities. When the agent takes an action in a state, there are many possible next states and rewards. The transition dynamics function P formalizes this notion. Given a state S and action A, P tells us the joint probability of next state S' and reward R. In this course, we will typically assume that the set of states, actions, and rewards are finite. But don't worry, you will learn about algorithms that can handle infinite sets and uncountable sets. Since P is a probability distribution, it must be non-negative, and its sum over all possible next states and rewards must equal 1. Note that future state and reward only depends on the current state and action. This is called the Markov property. It means that the present state is sufficient, and remembering earlier states would not improve predictions about the future. That's it for this video. In summary, MDPs provide a general framework for sequential decision-making, and the dynamics of an MDP are defined by a probability distribution. In the next video, we will discuss several decision-making tasks and formalize each as an MDP. When should we formulate a problem as an episodic or a continuing task? In this short video, we'll discuss a few more examples that will help us understand episodic and continuing problems. By the end of this video, you will be able to understand when to formalize a task as episodic or continuing. First, let's look at an example of an episodic task. Consider an agent learning to play a simple video game. The player, represented in blue, gets points for collecting white treasure blocks. The game ends when the player touches a green enemy block. This game is naturally represented as an episodic MDP. The agent tries to get a high score, collecting as many points as possible before the game ends. The state is an array of pixel values corresponding to the current screen. There are 4 actions: up, down, left, and right. The agent gets a reward of +1 whenever it collects a treasure block. And an episode ends when the agent touches one of the green enemies. Regardless of how the episode ends, the next episode will begin with the agent in the center of the screen with no enemies present. By the way, the agent you are currently watching was trained with Q-learning. It's pretty good at this game, isn't it? In Course 2, you'll learn about this algorithm and implement it yourself. Now let's look at an example of a continuing task. The agent is going to schedule jobs on a set of servers. Suppose we have 3 servers used by reinforcement learning researchers to run experiments. Researchers submit jobs with different priorities to a single queue. The state is the number of free servers and the priority of the job at the top of the queue. The actions are to reject or accept the job at the top of the queue if a server is free. Accepting the job runs it and yields a reward equal to the job's priority. Rejecting a job yields a negative reward proportional to the priority and sends the job to the back of the queue. The agent should be careful about scheduling low priority jobs since it could prevent high priority jobs from being scheduled later. The servers become available as they finish their jobs. The researchers continually add jobs to the queue and the agent accepts or rejects them. Since this process never stops, it's well described as a continuing task. That's it for this video. You've now seen some concrete examples of episodic and continuing tasks. Episodic tasks break naturally into independent episodes. Continuing tasks are assumed to continue indefinitely. You should now be able to determine which formulation is most appropriate for a given problem.
Welcome to week 2 of the Capstone Project. I'm Nico Yasui. I'm a grad student here at the University of Alberta, and I'm one of the creators of this specialization. So far, we've discussed a fun problem, landing a shuttle on the moon. We have formalized this problem as an MDP. This week, we will begin discussing how to solve this MDP by deciding which of the many algorithms you have learned about are a good fit for this problem. You might remember our course map that helped guide us through all the algorithms in course 3. Let's use it to decide what algorithm to use for this capstone. First step, can we represent the value function using only a table? Let's recall the state space of the lunar lander problem. The agent observes the position, orientation, velocity, and contact sensors of the lunar module. 6 of the 8 state variables are continuous, which means that we cannot represent them with a table. And in any case, we'd like to take advantage of generalization to learn faster. Next, ask yourself, would this be well formulated as an average reward problem? Think about the dynamics of this problem. The lunar module starts in low orbit and descends until it comes to rest on the surface of the moon. This process then repeats, with each new attempt at landing beginning independently of how the previous one ended. This is exactly our definition of an episodic task. We used the average reward formulation for continuing tasks, so that is not the best choice here. So let's eliminate that branch of algorithms. Next, we want to think about if it's possible and beneficial to update the policy and value function on every time step. We can use Monte Carlo or TD. But think about landing your module on the moon. If any of our sensors becomes damaged during the episode, we want to be able to update the policy before the end of the episode. It's like what we discussed in the driving home example. We expect the TD method to do better in this kind of problem. Finally, let's not lose sight of the objective here. We want to learn a safe and robust policy in our simulator so that we can use it on the moon. We want to learn a policy that maximizes reward, and so this is a control task. This leaves us with 3 algorithms, SARSA, expected SARSA, and Q-learning. Since we are using function approximation, learning an epsilon soft policy will be more robust than learning a deterministic policy. Remember the example where, due to state aliasing, a deterministic policy was suboptimal. Expected SARSA and SARSA both allow us to learn an optimal epsilon soft policy, but Q-learning does not. Now, we need to choose between expected SARSA and SARSA. We mentioned in an earlier video that expected SARSA usually performs better than SARSA, so let's eliminate SARSA. And that's it for this week. We have now chosen an algorithm which will provide the foundation for our agent. See you next week.
We just discussed 2 TD control methods, SARSA and Q-learning. In this lesson, we'll talk about another TD control method called expected SARSA. By the end of this video, you will be able to explain the expected SARSA algorithm. Recall the Bellman equation for action values. Here you can see the expectation over values of possible next state action pairs. Breaking this expectation apart, we see a sum over possible next states as well as possible next actions. SARSA estimates this expectation by sampling the next state from the environment and the next action from its policy. But the agent already knows its policy, so why should it have to sample its next action? Instead, it should just compute the expectation directly. In this case, we can take a weighted sum of the values of all possible next actions. The weights are the probability of taking each action under the agent's policy. Explicitly computing the expectation over next actions is the main idea behind the expected SARSA algorithm. Now let's look at the expected SARSA's learning update. Since expected SARSA is still based on the Bellman equation for action values, it uses the familiar form of learning update. The algorithm is nearly identical to SARSA, except the TD error uses the expected estimate of the next action value instead of a sample of the next action value. That means that on every time step, the agent has to average the next state's action values according to how likely they are under the policy. For example, with the following values in policy, expected SARSA would use a value of 1.4 for its estimate of the expected next action value. However, there is a huge upside to calculating the expectation explicitly. Expected SARSA has a more stable update target than SARSA. Let's look at an example to make this more clear. In this example, the immediate reward is deterministically 1. Both SARSA and expected SARSA start out with the true action values for the next state. Even in this idealized case, the next action sampling that SARSA does can cause it to update its values in the wrong direction. It relies on the fact that in expectation, across multiple updates, the direction is correct. By contrast, expected SARSA's update targets are exactly correct and do not change the estimated values away from the true values. In general, expected SARSA's update targets are much lower variance than SARSA's. The lower variance comes with a downside, though. Computing the average over next actions becomes more expensive as the number of actions increases. When there are many actions, computing the average might take a long time, especially since the average has to be computed every time step. In this video, we showed that the expected SARSA algorithm explicitly computes the expectation under its policy, which is more expensive than sampling but has lower variance. Several recent applications of reinforcement learning, learning to play Atari games, control traffic signals, or even automatically configuring web systems, have been built on a single algorithm. This algorithm is called Q-learning. By the end of this video, you will be able to describe the Q-learning algorithm and explain the relationship between Q-learning and the Bellman optimality equations. Q-learning was developed in 1989 and is one of the first major online reinforcement learning algorithms. Let's take a look at the pseudocode. We've seen this format before. The agent chooses an action in a state, takes the action, and observes the next state and reward. Then the agent does an update, and the cycle repeats. With so many familiar elements, what's new about Q-learning? Well, the new element in Q-learning is the action value update. Here, the target is the reward, RT plus 1, plus gamma times the maximum action value in the following state. This differs from SARSA, which uses the value of the next state action pair in its target. Why does Q-learning use a max instead of the next state action pair? This connection goes way back to the dynamic programming material. If you look at the update equation for SARSA, it's suspiciously similar to the Bellman equation for action values. In fact, SARSA is a sample-based algorithm to solve the Bellman equation for action values. Q-learning also solves the Bellman equation using samples from the environment, but instead of using the standard Bellman equation, Q-learning uses the Bellman optimality equation for action values. The optimality equations enable Q-learning to directly learn Q star instead of switching between policy improvement and policy evaluation steps. Even though SARSA and Q-learning are both based on Bellman equations, they're based on very different Bellman equations. SARSA is a sample-based version of policy iteration, which uses Bellman equations for action values that each depend on a fixed policy. Q-learning is a sample-based version of value iteration, which iteratively applies the Bellman optimality equation. Applying the Bellman optimality equation strictly improves the value function, unless it is already optimal. So value iteration continually improves its value function estimate, which eventually converges to the optimal solution. For the same reason, Q-learning also converges to the optimal value function, as long as the agent continues to explore and samples all areas of the state action space. Let's review what we learned today. In this video, we introduced the Q-learning algorithm and described its connection to the Bellman optimality equations.
Do we have to choose between directly learning the policy parameters and learning a value function? No. Even within policy gradient methods, value learning methods like TD still have an important role to play. In this setup, the parameterized policy plays the role of an actor, while the value function plays the role of a critic, evaluating the actions selected by the actor. These so-called actor-critic methods were some of the earliest TD-based methods introduced in reinforcement learning. After watching this video, you will be able to describe the actor-critic algorithm for control with function approximation for continuing tasks. We finished off the last video with this expression for the policy gradient learning rule. But we don't have access to QPy, so we'll have to approximate it. We can do the usual TD thing, the one-step bootstrap return. That is, the differential reward plus the value of the next state. As usual, the parameterized function v hat is a learned estimate of the value function. In this case, v hat is the differential value function. This is the critic part of the actor-critic algorithm. The critic provides immediate feedback. To train the critic, we can use any state value learning algorithm. We will use the average reward version of semi-gradient TD. The parameterized policy is the actor. It uses the policy gradient update shown here. We could use this form of the update, but there is one last thing we can do to improve the algorithm. We can subtract off what is called a baseline. Instead of using the one-step value estimate alone, we can subtract the value estimate for the state st to get the update that looks like this. V hat of st is the baseline in this case. Notice that this expression is equal to the TD error. The expected value of this update is the same as the previous one. Why is this? Let's take the expectation of the update conditioned on a particular state s at time t. Taking the expectation of the sum is the same as the sum of the expectations. We can use this to separate out the expectation of our original term from the expectation which involves the subtracted value function. It turns out the expectation of the second term is 0. So we can add this baseline to the update without changing the expectation of the update. You can verify this for yourself. To start, write the expectation as the sum over actions and pull the v hat term out of the sum. We'll leave this as an exercise. So why do we add this baseline if the update is the same in expectation? Subtracting this baseline tends to reduce the variance of the update, which results in faster learning. This update makes sense intuitively. After we execute an action, we use the TD error to decide how good the action was compared to the average for that state. If the TD error is positive, then it means the selected action resulted in a higher value than expected. Taking that action more often should improve our policy. That is exactly what this update does. It changes the policy parameters to increase the probability of actions that were better than expected according to the critic. Correspondingly, if the critic is disappointed and the TD error is negative, then the probability of the action is decreased. The actor and the critic learn at the same time, constantly interacting. The actor is continually changing the policy to exceed the critic's expectation, and the critic is constantly updating its value function to evaluate the actor's changing policy. With the policy update in place, we are ready to go through the full algorithm for average reward actor-critic. To start, we specify the policy parameterization and the value function parameterization. For example, we might use tile coding to construct the approximate value function and a softmax policy parameterization. We will need to maintain an estimate of the average reward, just like we did in the differential SARSA algorithm. We initialize this to 0. We can initialize the weights and the policy parameters however we like. We initialize the step size parameters for the value estimate, the policy, and the average reward. And they could all be different. We get the initial state from the environment and then begin acting and learning. On each time step, we choose the action according to our policy and receive the next state and reward from the environment. Using this information, we compute the differential TD error and update our running estimate of the average reward. We update the value function weights using the TD update. Finally, we update the policy parameters using our policy gradient update. And that's it. This algorithm is designed for continuing tests, so we can run it indefinitely and continue to improve the policy forever. That's it for this video. You should now understand that it is useful to learn a value function to estimate the gradient for the policy parameters, and that the actor-critic algorithm implements this idea with a critic that learns a value function for the actor. Bye for now.
Okay, so my name's Csaba Szepesvári, and I'm a professor here at the U of A teaching computing science. So one of the things is that, of course, if you want to have a solution, then you should know what your problem is, because your solution is going to be a function of the problem that you're working on. The other thing is that, well, you might think that this determines what you do always, but sometimes you just want to develop tools. And when you're developing tools, then you want to know which problems these tools fit, and which problems they fit well and which problems they are not fitting that well. So there are two important things that you should start with when thinking about problems to solve with reinforcement learning. First, you should be really clear about the goal that you have. And you can have different types of goals. You can have a goal of solving a specific type of problem, or just like some particular problem. Or you could be interested in developing some kind of tool, and then in that case, you should be clear about what are the goals in developing those tools, so where you want to apply the tools for. When it comes to specifying a problem, the things you should be thinking about are the following. You should be thinking about how the data is going to be collected, and how you're going to evaluate the algorithms that you're going to develop, and what are the specific properties of the environment, if any. And I'm going to expand on these. So when talking about the data that you're going to use in your algorithm, there are different types of problems depending on how you're acquiring the data. So maybe your system is going to interact with the real world, or maybe it's going to interact with a simulator, or there will be no interaction at all, and the data is going to sit on a disk. And depending on which situation you're in, you may need to choose very different tools and techniques, and you will have different concerns. So if your system is interacting with the real world, then of course the real world is running at our own speed, so data efficiency is going to be of a major concern. If you're interacting with a simulator, then maybe all you care about is how much compute you're going to use. Why, if there is no interaction at all, then you have all the data saved on a disk. Then you care about how much information you can extract from this data. So you will have different goals depending on where the data is coming from. And the algorithms that you will need to apply are going to, change accordingly. The other aspect of specifying what reinforcement learning problem you have is how you're going to evaluate your algorithms, right? So do you care about efficient learning? And if you do care about efficient learning, as probably you should, you care about how well your system is going to do at the end of the learning, or you're trying to develop a learning system that is also doing well during learning. So depending on which situation you're in, you might choose different algorithms. So the algorithm, for example, that cares about, like if you care about how well you're going to do at the end of learning, then your algorithm may do crazy exploration that may be very expensive in terms of reward while it's learning. But if you're in the second situation where you care about the reward collected during learning, then you may not want to do that much, right? So you will need to choose different solutions again. And finally, you will need to choose your performance metrics, and there's a wide range of possibilities there as well. You might care about total reward, maybe you want to use a discount factor, maybe you care about the risk sensitivity of your solution, maybe you care about performance across different environments in a worst case sense or average sense. Maybe you don't care about the reward, maybe you care about how much knowledge is acquired or what skills are acquired at the end of the learning period. So in all these different settings, you're going to evaluate your algorithm differently, and you might choose very different algorithms for different settings. And finally, it's also very important to think a little bit about the specific aspects of the environments that you're interested in dealing with. So the simplest of this is just like how many states and actions you have in the environment. So if you have, like a large number of states, are there any irregularities between the states that you can exploit? If you have a large number of actions, then if you have continuously many actions, then some algorithms become unavailable because they're not able to deal with those settings. But if you have finitely many actions, small number of actions, then maybe suddenly those algorithms become available, so you may want to choose them. And the other aspect could be that maybe the rewards in the environment or the costs can blow up, so they can become unbounded, and then you don't want to run the risk of facing unbounded costs. Maybe the rewards are random, or the environment is random, or maybe it's not. And again, if the environment is not random, then you can have specialized algorithms that take advantage of that. The problem is much simpler. So all of these aspects of the environment are pretty important, and you will choose your algorithm based on what situation you're in. And why is this important, you may ask? Just as an illustration, just think about a simple bandit problem where you have maybe two arms, and the underlying distribution of the arms, is stochastic bandit, are unknown. But if you happen to know that the distribution belongs to a specific family, like you have normal distributions, or you have Bernoulli distributions, then you will choose algorithms that depend on these distributions, and distribution depends on the knowledge that you have about these distributions, and your algorithm will do much better if you exploit these properties. So in a nutshell, it's important to be clear about what is the problem that you're solving, for the sake of choosing the right algorithm, and also for the sake of, just for the sake of clarity of the scope of your solution is going to depend on this, and you want to be clear about that.
So back to risk seeking and risk aversion. My risk aversion has led me to look at what people in the past have done, because I don't like to risk someone saying, oh, that's just this that we did 30 years ago. And I sort of always driven to prevent that from happening. And so I look back, I've become the historian of the field to some extent. I mean, with Rich's help too, of course, but and that's what fascinates me. I love how these things are connected, and this fabric, the dynamic programming and control and prediction and all these things, not to mention the psychology and neuroscience. I mean, those kinds of connections fascinate me. So in that article in AI, magazine, I repeated what I said at the first RLDM meeting. I did some opening remarks. And I said, if you reinvent the wheel, and there's a lot of wheel-like stuff in RL, call it a wheel, or maybe an improved wheel rather than something different, because that's what connects this field to the whole body of, it's moving forward in terms of increasing one's armament of algorithms and techniques and so on. So, don't give it some name that doesn't connect to anything.
I wanted to ask you about this. I mentioned how growing up as a graduate student, you were an important influence on me and the things that I've learned from you and still continue to learn from you. And one of the big things is just scholarship. It's just, when I grew up with you, and I wrote things, and you would tell me things like, you would call you called it purple prose, and I was just too effusive, and you wanted to rein me in and make me more accurate and more respectful of my predecessors. And this is something that I think I've learned from you, and I've now tried to pass it on to others. Scholarship and craftsmanship. I know you are also a carpenter. And I just wondered how you became this way, and how you think about the craftsmanship and scholarship of being a scientist.
Well, so your mom taught writing.
Yeah, that's
and
true.
I gave you a hard time on the draft of your thesis. So he comes back with a stack of books on writing, like this high, on his desk. And now he's an extremely good writer, and my students still complain about that. I mean, I can't read.
They complain about my being a good writer?
No, about me.
Why do you teach
hassling
people to be a
them.
good writer? It's important.
I mean, I can't focus on the technical stuff unless I can, unless the writing is decent. It drives the students nuts, but they're better for it. I don't know. Well, craftsmanship. Yeah, I guess I like. I'm a perfectionist in some sense, and that's why the errors in our book really bug me. But I like it. I like something to be a lasting thing that I don't have to keep fooling with, and finished product. And Rich posted our drafts on the internet, which I really didn't like. And it yielded a lot of wonderful comments. But I'm like, oh, it's not perfect. I don't want other people reading that. So Rich, put it all out there, and that's fine. But I would have preferred to spring a perfect book on people at the end. I don't know. I mean, so is it risk aversion as well that leads to? I mean, when I work with my hands building something, if there's a little mistake, if I don't fix it, it bugs me whenever I look at the product. Years later, oh, there's that little thing.
Well, I think it's a very timely thing for our field because there's a feeling that we want to move faster because things are heating up, and so there's this tension between the desire to get done faster, to get somewhere faster, and do something lasting.
Hi, I'm Drew Bagnell, the Chief Technology Officer at Aurora Innovation. In the second lecture, I'll give you a quick introduction to the process of learning models within model-based reinforcement learning, with an emphasis on approaches you might find practical. Okay, last time we discussed the key benefits of using a model, the ability to learn in simulation and thus greatly reduce the expense and time of real-world interaction. Of course, the key to make that happen is we need the ability to learn a model. For the rest of this lecture, we're going to use as an example the problem of autonomous helicopter control. In this case, what's known as a nose-in funnel. And we want to learn a model from observations so that we can apply optimal control to, for instance, this given task. The traditional view of this is known as system identification, and it's taught in engineering statistics, is essentially a supervised learning approach. We have some way of collecting data using an exploration policy. For instance, for a pilot who controls the helicopter and induces deviations in those controls to explore the space of states. We then take that observed data and we apply a supervised learning algorithm. Imagine, for instance, applying linear regression. Given that supervised learning algorithm, the data, we're learning a model, here called t-hat, which maps states and actions to next states. We take that model, we take a cost function, we combine them together using planning or optimal control synthesis algorithms, reinforcement learning algorithms, if you will, and we output a learned policy which is hopefully optimal in the actual world. In practice, what we find is this is not actually what good engineers do. Instead, they tend to take an iterative approach to building the model. Let's see why. In this example, we begin by collecting data from expert demonstration of this nose-in funnel. And we collect a variety of examples of it doing this task. Then we apply the class of optimal control algorithms we talked about in the last lecture to try to generate a policy. And what you find is, unfortunately, it fails pretty spectacularly. Now, why does this go wrong? Well, fundamentally, the problem of system identification is really a chicken or the egg problem. We really want to learn a model that's good where the RL algorithm, or optimal control synthesis algorithm, is likely to visit as it learns a policy. Unfortunately, if we learn a model and then plan or optimize against it, we'll almost certainly visit states in the process where the model was inaccurate. They were undersampled during the data collection procedure. And then the RL algorithm can find any way to exploit that inaccuracy, and it'll learn a policy that doesn't perform well because the real world doesn't match the model in those states. This general problem is sometimes known as covariate or distributional shift, and it's really a fundamental problem whenever we blend statistical learning with decision making. The result is, both in theory and practice, you can build statistical models of dynamics with very low error, apply a good optimizer or RL algorithm to that model, and still get bad performance in the real world. That's really a bummer. I find a really useful way to think about model-based reinforcement learning is as a two-player game between the optimizer and RL algorithm and the model learning and the world together. As I learned years ago from Chris Atkinson, the best way to find an inaccuracy in your simulator is to let an RL algorithm try to exploit it, to find a loophole in your model, a glitch in the matrix, if you will. We thus need approaches that are more robust and fundamentally interactive to find good models and good controllers. I'll take you through an approach here which is fundamentally interactive. And the idea is that we will collect data from our purported current optimal policy as well as that exploration policy I described before. We'll get transitions that describe the way the helicopter goes from a state, takes an action, and goes to the next state. We'll aggregate that together with all the previous transitions that we've had. Again, this is an iterative algorithm. We'll fit a model. Again, I'm showing here fitting linear regression. Then we'll hand this off to an optimal control synthesis approach, or a planner, or a reinforcement learning algorithm, if you will. And the result will be a new policy, a new purported optimal policy. And then we run this loop again, collecting data from the new policy, together mixed with some data from the exploration policy. All of those transitions are aggregated together with everything we've previously seen before. We fit the model, hand it off to the synthesis, which hands back a purported new policy, and continue in this loop. It turns out if you run this loop, Stefan Ross demonstrated that this kind of interactive approach, which turns out to much more closely match the style used by expert engineers, works really well in practice, and it can provide stronger theoretical guarantees. If you learn a low error model across iterations of interaction using a stable function approximator, and you generate policies using a good optimal control solver, you must achieve good performance. And put in the contrapositive, to not get good real-world performance using a no-regret learning algorithm, the class of algorithm we're talking about for learning, a good optimizer against that model, it must be the case that at some point you failed to build a low-error model of how the world works. There's lots of details to these statistical guarantees, but they indicate that stable learning and on-policy model learning are probably on the right track. I mentioned briefly this idea of no-regret learning. It's a powerful concept worth learning about and it's very useful in any context which seems game-like. And you can simplify it in your head to the class of algorithms that don't change the model they return much in response to small perturbations in their training data, and which achieve good performance in the limit of large data. Okay, we can take that same inverted, or rather nose-in funnel problem I described before, and apply this loop we described. And here's the results. We'll collect the same number of samples using this dataset aggregation approach. And in this case, we'll be able to actually solve the problem. So this is interesting. The only thing that's different, same synthesis algorithm, same number of samples, all that's different is we've collected data in an interactive way where we've proposed optimal controllers, tried them, collected more data, and then rebuilt the model. And the result is we're successfully able to execute the nose-in funnel. I thank you for your attention, and I really hope these lectures give you a head start on ideas for applying models and reinforcement learning in the real world.
Hi everybody, I'm Susan Murphy. I'm at Harvard University. I'm joint in statistics and in computer science. And what I do is I work in mobile health. And in particular, I work on how we can use reinforcement learning in mobile health. And on the slide in front of you, you can see all the different kinds of ways, the kinds of studies that we've been involved in. Many of the studies involve addictions, a lot of them involve adolescence, and so on. So in mobile health, what do we want to do? What we want to do is we want to help people who are struggling with a problem. Often these are chronic illnesses, like someone who's struggled with addiction, and how are they going to stay clean? It might be someone who's struggling with depression, and so on. So long-term support to someone. We also want to be able to test causal inference. So we really want to understand, does this treatment action, an action in the case of RL, does it really impact that person or not? Also in mobile health, we think about how we can continually learn. We can continually experiment so that we can always improve the mobile health application for each person. And that's what this slide is talking about. So what's the basic setup? So for any given user, they can receive a whole variety of interventions, that is actions. I listed some on the slide. You see reminders, maybe reminders to take your medication, reminders to practice certain types of exercise, and so on. Suggestions about what you can do in your life, how you can link you up with someone else who's been through similar problems, and so on. And this can happen repeatedly over time. After each time we deliver a different type of action, treatment action, we observe a reward. So the reward could be, for example, total step count over the next 30 minutes if I'm trying to help you be more active. Could be how long it is until you become stressed again if the app is trying to help you manage your stress. On the next slide, I'm going to show you a study that just finished. And in this study, our goal was to help people be more active in answering questions about their stress and loneliness. And this study recruited young adults, adolescents, and college students age, not always college students, who were in trouble. They were recruited out of our emergency room because they had been drinking too much. And the idea was, if we can learn about what their feelings of loneliness or how depressed they are, then we can develop an app which helps them manage that. So all the actions in this RL problem have to do with how do we give you reinforcements so that you will stay engaged and answer our questions. You can see we had a gamified interface. It was an aquarium, and as you answered questions, you built your aquarium became more and more rich, and you also could level up to higher levels in the aquarium environment. But I was mostly interested in how do we provide rewards to you if you answer questions. That's the top line in this diagram, whether or not what kinds of rewards, memes, gifts will help you be more engaged so you'll answer our questions tomorrow. I was also interested in, if we give you a gift, a present today, are you more likely to answer our questions this evening? So the whole goal of this study is to find good policies for how we keep people engaged in answering questions about their life. So what are we doing now? We're using these kinds of studies to initialize reinforcement learning algorithms in mobile health. And the idea here is that the reinforcement learning algorithm should personalize the app to each user. From our perspective, yours and mine, this is the same as learning an optimal policy for each user. In our lab, in my lab, we mainly use Bayesian reinforcement learning. I don't think you've learned about Bayesian reinforcement learning, but the main tool for us, one of the main advantages of Bayesian reinforcement learning is the way it updates information on an individual user over time. And also, it selects actions at each time in a random way, stochastically. And this helps us learn from the data after the study is over as well. So what are the challenges to reinforcement learning when you try to use it in my setting, that is in mobile health? Well, one of the issues is, if you've ever downloaded an app, you know exactly what I'm talking about. It can get really aggravating when the app notifies you a lot. So normally, apps have a lot of potential to help you in the moment. So positive effects on the immediate rewards, but negative delayed effects. This is the classical setting for reinforcement learning. Some of the things we have to figure out how to do are how to approximate the value function so that we can learn fast yet not make mistakes in choosing actions. If we always have many users, they're all very different, each person is different, but how can we use one user's data to personalize or find or determine a good policy for each particular user? This is a big challenge we're working on now. Also, after a study is over, we always want to conduct causal inference. That is, we want to help scientists learn more about how to why people enact certain behaviors. Why do people relapse to drug use? Why do they relapse to smoking? These are causal inference questions. How can the treatment help them so that they don't relapse? So we want to use this data to do this. And we want to, even though the data is collected via a reinforcement learning algorithm, we want to use the data for that. And we have to figure out how. And then how can we use data from the current study for future users so that they will be able to benefit from what we learn from the current study. Okay, I want to show you, this is my next slide, it's my last slide, and I want to show you one more study. This study is pretty cool, it's almost over. And in this study, each person is trying to quit smoking. The study starts on the day they decide they are going to quit. And they're wearing a whole variety of wearables. And they go through their whole life and all this sensor data is streaming in. And the sensor data is used to form a whole variety of predictions. And one prediction in particular is whether or not they're currently physiologically stressed. And we're using algorithms to test whether or not, if you're currently stressed, we should provide a reminder to practice stress management exercises. Of course, the long-term goal is to find an optimal policy for each user. Thanks. Good luck on your class. Bye.
Welcome to the second last week of the Capstone project. This is an exciting time because you finally get to start building your agent. Last week we brainstormed some of the high-level agent design choices. This week we will discuss a few implementation details regarding the network and how to update it. In practice, these decisions can have a big impact on performance. Today we will discuss how we will update our estimates of the action values and the details of the ADAM algorithm. We decided to use a neural network for the action values, but let's refresh your memory on how that works. You may recall from course 3 that the neural network takes the state and produces a new representation. For instance, in this case, the state would be composed of things like the position and velocity of the lander. We'll then use the resultant representation to estimate the value of each action. We do this by building a network that has one output node for each action. Let's discuss how to train this neural network to approximate the action value function. We will use the TD error to train the network. More precisely, we will modify the weights to reduce the TD error on each time step. We will only update the weights for the output corresponding to the action that was selected. We simply do not update the weights in the last layer for the actions 2 and 3. You might ask, is this a problem? In general, no, but there are some nuances to consider here. For linear function approximation, we also maintain separate weights for each action value. We only updated weights for the action that was taken. With the neural network, each time an action is updated, the shared representation for all the actions is also changed. But during learning, the result of each action might cause different, possibly conflicting updates to the representation. But this is actually something that we want. We want the neural network to learn a representation that is useful for all the actions. Features that are good for multiple predictions are often features that generalize better. In contrast, we could instead learn completely separate neural networks, one for each action. But then the representation for each action is learned with fewer samples, and we can't gain the potential benefits from learning a shared representation. The other decision we made was to use the ADAM algorithm. This algorithm combines both vector step sizes and a form of momentum. In course 3, we discussed a vector of step sizes. Each weight of the network has its own step size, adapted based on the statistics of the learning process. This means we can make larger updates to some weights and smaller updates to the others. This might be useful if the loss is flatter in some dimensions. Alternatively, we can take smaller steps in other dimensions where the loss changes more sharply. We also discussed how to use momentum to accelerate our learning, especially if we find ourselves in a flat region of our loss. Remember that taking repeated steps in the same direction builds momentum, while taking steps in a different direction will kill the momentum. The ADAM algorithm combines both of these ideas. It keeps a moving average of the gradients to compute the momentum. The beta m parameter is a metaparameter that controls the amount of momentum. ADAM also keeps a moving average of the square of the gradient. This gives us a vector of step sizes. This update typically results in more data-efficient learning because each update is more effective. You may have noticed that we just introduced several new metaparameters that we will need to set. We have the 2 decay rates, the size of the small offset in the denominator, and a global step size. So we haven't achieved metaparameter-free learning here. In fact, we have introduced 4 metaparameters in place of 1. Fortunately, it is typically not too difficult to find good settings for these metaparameters using rules of thumb. But better performance can usually be achieved by tuning them individually. Many people are working on methods to reduce the sensitivity to metaparameter choices in reinforcement learning, but this is still very much an open problem. In this capstone, you will investigate the impact of different choices of the global step size. We will use fixed values for the other parameters. And that's it for this week. You should now have all the tools you need to implement your agent. Next up, landing a shuttle on the moon with reinforcement learning.
Supervised learning systems based on deep neural networks are now the go-to solution for image classification, speech recognition, and natural language processing. Part of the reason is due to the dramatic increases in training data and affordable computation. But to really take advantage of these increases in data and computation, improvements in training were needed. A couple of simple optimization strategies made it much easier to train networks and helped accelerate adoption. We'll talk about these today. By the end of this video, you will be able to understand the importance of initialization for neural networks and describe optimization techniques for training neural networks. Like many machine learning methods, neural networks are trained using an iterative process. This procedure must have some starting point. The choice of this starting point can play a big role in the performance of the neural network. Let's look at an example with only one weight. On the y-axis, we will show the loss function. On the x-axis, we will show values of the weight. As you know, gradient descent will iteratively move the weight towards the nearest stationary point. But neural network loss functions are not quite so simple. If we start in this nearly flat region, it can be hard to make any progress with gradient descent, since the gradient is near zero. If instead we start inside this small bowl, then we can quickly find the local optima. But wouldn't it be nice if we could start somewhere here, where we can quickly find an even better optimal point? One simple yet effective initialization strategy is to randomly sample the initial weights from a normal distribution with small variance. This way, each neuron has a different output from other neurons within its layer. This provides a more diverse set of potential features. By keeping the variance small, we ensure that the output of each neuron is within the same range as its neighbors. One downside to this strategy is that as we add more inputs to a neuron, the variance of the output grows. We can get around this issue by scaling the variance of the weights by 1 over the square root of the number of inputs. After we have picked the starting point for our network, we start incrementally making small improvements to the weights using stochastic gradient descent steps. Another way to improve training is to consider more sophisticated update mechanisms. Two common strategies are to use the heavy ball method, also called momentum, and vector step size adaptation. Let's talk about momentum first. Imagine this is the trajectory of a two-dimensional weight vector under stochastic gradient descent. Here is the stochastic gradient descent update rule. And here is the update modified to include momentum. Notice it is similar to the regular stochastic gradient descent update plus an extra term called the momentum, m. The momentum term summarizes the history of the gradients using a decaying sum of gradients with decay rate lambda. If recent gradients have all been in similar directions, then we gain momentum in that direction. This means we make a large step in that direction. If recent updates have conflicting directions, then it kills the momentum. The momentum term will have little impact on the update, and we will make a regular gradient descent step. Momentum provably accelerates learning, meaning it gets to a stationary point more quickly. Another potential improvement is to use a separate step size for each weight in the network. So far, we have only talked about a global scalar step size. This is well known to be problematic because this can result in updates that are too big for some weights and too small for other weights. Adapting the step sizes for each weight based on statistics about the learning process in practice results in much better performance. Now, how does the update change? The change is very simple. Instead of updating with a scalar alpha, there's a vector of step sizes indexed by t to indicate that it can change on each time step. Each dimension of the gradient is scaled by its corresponding step size instead of the global step size. There are a variety of methods to adapt a vector of step sizes. You will get to implement one in your assignment. That's it for this video. Today we discussed ways to improve the training of neural networks. Specifically, we discussed one strategy for initializing the weights in a neural network and how to accelerate learning using momentum and step size adaptation. Now you're all set to implement a TD agent with a neural network. Hope you have fun!
So far, we've talked about using SARSA with function approximation. Let's continue our journey through approximate control methods and look at expected SARSA. By the end of this video, you'll be able to explain the update for expected SARSA with function approximation and explain the update for Q-learning with function approximation. Let's see how we can turn SARSA into expected SARSA when using function approximation. Recall the update equation for SARSA. SARSA's update target includes the action value for the next state and action. Now recall that expected SARSA instead uses the expectation over its target policy. To compute the expectation, we simply sum over the action values weighted by their probability under the target policy. The same expectation can be computed even when we use function approximation. Let's see how to do this. First, recall the update for SARSA with function approximation. It looks similar to the tabular setting, except the action value estimates are parameterized by the weight vector W. We also have a gradient term to distribute the error to the weights appropriately. Expected SARSA with function approximation follows a similar structure. we compute the action values from a weight vector for every action in the next state. Then we compute its expectation under the target policy. And that's all we have to do to change SARSA into expected SARSA. Now, how do we do this for Q-learning with function approximation? Fortunately, Q-learning is a special case of expected SARSA. In Q-learning, the target policy is greedy with respect to the approximate action values. Computing the expectation under a greedy policy is the same as computing the maximum action value. So the Q-learning update with function approximation is actually quite straightforward. We just use the max in place of the expectation. And that's it for this short video. Today, we introduced expected SARSA with function approximation, and we also showed how to extend it to Q-learning with function approximation. Next time, we'll think about how to do exploration with function approximation. Until then, don't get lost. We've discussed the Dyna architecture and how it combines planning, learning, and acting. We have also studied how DynaQ operates in a grid world. Let's get down to business and run some experiments to see how well DynaQ really works. In this video, you will use a small grid world to compare tabular DynaQ and model-free Q-learning. By the end of this video, you will be able to describe how learning from both real and model experience impacts performance. You will also be able to explain how a model allows the agent to learn from fewer interactions with the environment. Today, we'll run some experiments on this small maze environment. Like before, the agent has 4 actions. Transitioning into the goal state generates a reward of +1. All other transitions generate a reward of 0. This problem is episodic, and we will use a discount of 0.95. Let's compare DynaQ with different amounts of planning. We will compare 3 agents. Each one will use alpha equal to 0.1 and epsilon equal to 0.1. We initialize the action value estimates to 0 for all 3 agents. We ran the experiment for 50 episodes, 30 times, and then averaged the results. Let's have a look. We can plot the average number of steps the agent took to complete each episode after more and more episodes. If the agent is doing well, then the number of steps should decrease with more episodes. That is, lower on the y-axis is better. If we run DynaQ with 0 planning steps, we get exactly the Q-learning algorithm. As we can see, it slowly gets better, but plateaus at around 14 steps per episode. If we run DynaQ with 5 planning steps, it reaches the same performance as Q-learning, but much more quickly. DynaQ with 50 planning steps only takes about 3 episodes to find a good policy. DynaQ is far more sample efficient. Look at the y-axis. After 2 episodes, the policy found by Q-learning still requires hundreds of steps to escape the maze. For the same number of environment interactions, DynaQ can learn a lot more. This shows how planning makes better use of environment experience if the model is correct. Let's visualize what's going on in a slightly different maze. We use an arrow to show the greedy action according to the estimated value in each state. A state without an arrow means that every action is equally likely under the policy. After 1 episode, Q-learning updates just 1 action value, the one corresponding to the up action in the state next to the goal. This is the only state where a transition with the non-zero reward was experienced. It would take several more episodes to bootstrap this state's value back to other nearby states. Let's look more closely at how search control impacts planning. Our robot will do things slightly differently than DynaQ, but that's just to emphasize our point more clearly. We will start with 10 planning steps and call the planning loop 10 times in a row. So that's 100 steps of planning in total. As you can see, many of the planning updates fail to change the value function. In fact, the agent only updated the values of 2 state action pairs after 100 steps of planning. Let's keep going. This time, we will try 100 planning steps per call and let the agent run a bit longer. Even with the 100 planning steps, the first few calls update only a handful of action values. Why does the agent need so many planning steps to learn the value function and a reasonable policy. The agent needs many planning steps because search control samples state action pairs randomly. The planning update will not have any effect if the sampled state action pair produces a 0 TD error. This happened a lot in this environment because all the rewards are 0, and so are the initial values. What would happen if we ordered the state action pairs in a more efficient way? It turns out the agent could learn a good policy only using 1/6 of the planning updates. In larger environments, random search control becomes even more problematic. If you want to learn more about this topic, check out section 8.4 of the textbook. In this video, we tested the tabular DynaQ algorithm in a simple grid world. We saw how planning can dramatically speed up learning. In our experiment, the more planning we did, the better the agent performed. Bye for now.
In course 3, the agents you implemented update the value function or policy only once with each sample. But this is likely not the most sample efficient way to use our data. You have actually seen a smarter approach in course 2, where we talked about Dyna as a way to be more sample efficient. But we only talked about Dyna for the tabular setting. In this video, we will talk about how to make your agent more sample efficient when using function approximation. We will discuss a simple method called experience replay and how it relates to Dyna. To get some intuition for experience replay, let's first remember a method that we know well, DynaQ. The idea is to learn a model using sampled experience. Then, simulated experience can be obtained from this model to update the values. This procedure of using simulated experience to improve the value estimates is called planning. To focus on the key ideas in Dyna, we made a few simplifying assumptions. Namely, DynaQ assumes deterministic transitions for a relatively small state space. For this setting, learning the model was simple. For every visited state action pair, we record the observed reward and next state. This only works in the tabular setting, where the number of state action pairs is small enough to fit into computer memory. If we were to attempt this in a continuous state domain, we would have an infinite amount of state action pairs to store. Worse than that, we will not see the same state twice if the world is stochastic. One option is to learn a model using all your new knowledge about function approximation. For example, you could learn a parameterized function that inputs states and actions and outputs next states and rewards. Unfortunately, even small errors in such a learned dynamics model seem to cause serious issues. It remains an open research question how to effectively use learned models in an RL agent. Fortunately, there is a simpler option for your capstone. Experience replay is a simple method for trying to get the advantages of Dyna. The basic idea is to save a buffer of experience and let the data be the model. We sample experience from this buffer and update the value function with those samples, similarly to how we sample from the model and update the values in Dyna. The key choices for experience replay are the size of the buffer, what experience to store, and how many updates to execute per step. Let's first take a look at how we store the experiences. For simplicity, let's go back to the tabular grid world. As we interact with the world, we observe a state, action, reward, next state tuple. We add these experiences to a buffer that we'll call the experience replay buffer. As we continue interacting with the world, we add more samples to this buffer until we eventually fill it up. When this happens, we can pick an older experience to delete and replace with a new experience. We also need to consider the size of our buffer. By allowing the buffer to be really large, we can remember potentially useful transitions from many time steps ago. However, the agent does have practical limitations. We will need to consider the amount of memory used by large buffers and any computational impacts from storing and accessing large buffers. Once we have decided to store a buffer, a natural idea is to use mini batches. Using a single sample from the experience replay buffer can produce a noisy update. Instead, we can use several samples from the buffer to create an average update to reduce that noise. The small collection of samples from the larger buffer is called a mini batch. The mini-batch update simply involves averaging the updates across the k random samples in the mini-batch. Here's an example computing this average update for Q-learning. We store the average update in a variable, let's call it U-bar. Then we grab several samples from the buffer and compute the Q-learning update for each sample. Finally, we average those updates to get the mini-batch update. Putting it all together, we get the following pseudocode for experience replay. As in Dyna, we can think of the planning steps occurring in the background. The agent can perform several of these planning updates, which are the replay updates, per each real step in the environment. More updates means we extract more from the data we have observed. Each of these replay updates consists of a mini-batch update to reduce the noise of that update. And that's it. Experience replay allows the agent to make better use of its data and so be more sample efficient. Further, it makes sure that the agent is updating in many parts of the environment, just like in Dyna. This week, you will see how to use experience replay within your agent.
This is it, the final week of the capstone project. After completing this week's notebook, you will have successfully implemented a complete reinforcement learning system, from problem specification to careful selection of metaparameters. Today we'll discuss that careful selection of metaparameters part. Recall all the key performance parameters that we identified in an earlier part of the capstone. We need to pick good values of each of these if we have any hope of building a successful learning agent. In practice, we will likely have to use rules of thumb for many of these choices. However, in some cases, we have the opportunity to study the impacts of the parameters to gain insight. For example, when learning in our simulator, we can test our agent with many different configurations of the parameters. This can help us identify a good range for a particular parameter. This might also help us set the parameter when we deploy the agent on the moon. In research, we might test our algorithms in a variety of simulated problems with many different parameter settings. This can provide insight into how our algorithms might behave in general. Running such scientific studies is not just useful for scientists, but it's also useful in industry too. In both cases, it is important to truly understand the methods you deploy. Let's think about how we might better understand how our algorithm behaves with different parameters. We can pick a range of each parameter and test several values in that range. We can visualize the results with a parameter sensitivity curve. On the y-axis, we have some performance measure. For example, if we ran the agent for 50 episodes, this measure could be the sum of the returns over these 50 episodes. We call this the total return. We then average this across multiple runs to get an average total return. On the x-axis, we have the values of the parameter we are testing. We do a complete run for each value of the metaparameter. This means we run the agent for the allocated number of steps, say 10,000 steps, for the desired number of runs, say 30 runs. We compute the total return for each run and average those numbers over 30 runs. We plot these averages for each chosen metaparameter to obtain this sensitivity curve. This curve provides insight into how the algorithm behaves for a range of its metaparameters, as well as how difficult it might be to pick those parameters. If the curve is very pointed, then it indicates there is a narrow range of good parameters. If you did not know this ahead of time, then it is unlikely you would find this good parameter setting. Even if you manage to pick a metaparameter very near the best one, the performance could be much worse. So, even though in the best case the algorithm can perform well, in practice it could perform significantly worse. You might think, well, once I have found this good setting, I can just use that metaparameter and get the good performance. Unfortunately, for a new problem, the best metaparameter is likely different. Rather, this analysis suggests you might have a hard time picking the metaparameter, so we need to be careful in deployment. On the other hand, if the range of good parameters is broad, then it is more likely you will be successful in choosing a good one. Further, it might indicate that your algorithm is not too sensitive to its metaparameter in general. This is even more likely to be true if you observe similar sensitivity to the metaparameter across problems. We do have to pay attention to a couple factors to produce meaningful curves. First, we have to test a sufficient number of values for the metaparameters. Otherwise, our approximation to the true parameter sensitivity curve will be poor. To see why, imagine that the true curve with respect to alpha looks like this. If we subsample only a few points to test, we may accidentally jump over the best value of those parameters. We also need to test a sufficiently wide range of the parameters. If we choose a range that the best value is at one end of the range, we may miss out on better values of the metaparameter. Don't worry, we will not ask you to exhaustively test each combination of the metaparameters. You will only get to sweep over one of the parameters for your expected SARSA agent. That way you will gain some experience doing a parameter study, but you won't have to wait hours for your program to run. We will suggest good values for the remaining parameters. It is important to note that we do not use parameter sweeps to actually select parameters for real problems. Rather, this is a strategy for understanding our algorithms in simplified settings. It is typically not feasible to systematically test the agent with many metaparameters. How can we test landing the module on the moon over and over with bad metaparameter settings that might cause repeated crashes? You would be fired in no time. It is so important to understand our algorithms and how they might behave. This is especially true in deployment in the real world, or in this case, in outer space. And that's it for today's video. Good luck in the final part of the capstone project. In the last few videos, we introduced TD and discussed its advantages over dynamic programming and Monte Carlo. In this video, we will dive deeper and compare TD and Monte Carlo in a carefully constructed scientific experiment. By the end of this video, you will be able to identify the empirical benefits of TD learning. Consider this simple MDP. We have 5 non-terminal states. In each state, we have 2 deterministic actions, left and right. Let's evaluate the uniform random policy. We want to estimate its value function. All episodes start in state C. Episodes terminate either on the left or on the right. The reward is 0 on all transitions, except +1 for terminating on the right. Let's set the discount factor to be 1. In this problem, the value has an intuitive meaning. The value of each state is the probability of terminating on the right when starting from each state. The value of the start state is 0.5. That means the probability of terminating from the center is a half. Randomly wandering from the center has a 50-50 chance of terminating on either side. That makes sense. Let's label the rest of the states with their values. Let's run an experiment right now. We have labeled the MDP with the true values at the top of the slide. The agent, our cute little robot, estimates the value function using TD. At the bottom, we have a Monte Carlo agent. Let's initialize the approximate value function for both agents to 0.5. Let's look at the performance of both agents during the first episode. Notice the TD agent only updated the value of state E. To understand this, consider the transition from state C to D. The TD error is equal to the reward on the transition plus the value of the next state, D, minus the value of state C. The reward is 0 because this is a non-terminal transition. The values of C and D are both 0.5. So the TD error is 0, and we make no change to the estimate for C. The same thing happens on every step except the transition into this terminal state from state E. In contrast, Monte Carlo updated the values of all the states the robot saw during the episode. Let's look at the next episode. Pay attention to how the values are updated during the episode. Eventually, the TD agent makes updates to the values on every step. In contrast, the Monte Carlo agent waited until the end of the episode before it made its updates. Let's look at a few more episodes.
The value estimates of the TD agent seem to be moving towards the true values. This is taking too long. Let's jump ahead and evaluate the asymptotic performance. Let's plot the estimated values at several points during learning. The x-axis represents each state in the MDP. On the y-axis, we have the estimated value. Here are the true values. Let's also plot the initial value estimates. Recall, we initialized them to 0.5. The red curve shows the values learned after the first episode. By the end of the first episode, TD only updated the value of a single state, as we discussed. The estimates after 100 episodes are about as good as they're ever going to get. Remember, we're using a constant step size of 0.1. This means the values will fluctuate in response to the outcomes of the most recent episodes. If we use a smaller learning rate, or better yet, a decaying learning rate, we might get a better estimate. A natural next question is, does TD learn faster than Monte Carlo? Let's compare the performance of TD and Monte Carlo on our example problem. Here, the x-axis represents the number of episodes. The y-axis represents the root mean squared error between the value function and the learned estimates. The red learning curves represent the performance of Monte Carlo for several values of alpha. Each curve is averaged over 100 independent runs. For instance, this point represents the average error achieved after 50 episodes for the learning rate 0.01. Now let's look at TD's performance. We see that TD performed consistently better than Monte Carlo. Let's look a little more closely. Notice the error reduces faster with a learning rate of 0.15, but ultimately results in higher final error. With a smaller learning rate, TD learns more slowly, but achieves lower final error. In summary, we ran a careful experiment comparing TD and Monte Carlo, and the results suggest that TD converges faster to a lower final error in this problem. See you next time.
Hello, my name is Joëlle Pinault, and I'm a faculty member at the School of Computer Science at McGill University, and I'm also a research manager at the Facebook AI Research Lab in Montreal. It's my pleasure to be here today and tell you a little bit about some of the work we've been doing on the issues of building systems that are reproducible, reusable, and robust, in particular for reinforcement learning. And so it may be interesting to you to know, why do I tie these three R's together? What do they have in common? And let me draw from this quote from the National Science Foundation that says that reproducibility actually refers to the ability for a researcher to duplicate the results of a prior study using the same materials that were used by the original investigator. And reproducibility is also the minimum necessary condition for finding to be believable and informative. And so as scientists, all these components are actually very important to how we practice science, but it's also very important in terms of how we share the findings from our work. There's been talks of this reproducibility crisis in science broadly, not just in machine learning. And so the journal Nature ran a very interesting study in 2016, surveying 1,500 or so scientists, asking them whether they thought there was a reproducibility crisis in their field. And a large number of them said, yes, there's either a slight crisis or a serious crisis going on. Now, in some of our work, we've been trying to figure out, it's one thing to be alarmist and answer some surveys, but then it's also another thing to look carefully at what the data tells us when we conduct our own comparisons. And in the case of reinforcement learning, it's been very impressive, the rate of progress we've seen in the last couple of years, really. Systems demonstrating the ability to play, in many cases play games, at a performance level exceeding the best humans. And where we thought some of these games were really difficult, might be decades away from solving, we've had some impressive results, in particular on the game of Go, but also on some challenging video games, where RL-trained systems are able to achieve these really good results. Doing well in games and simulation is wonderful. It really makes us see the potential for the technology. But what we care about in the long term is really how well can this technology, RL algorithms, help us solve real-world problems. And so an attempt to understand how far the science has come and how close we are to solving these hard, difficult real-world problems, we started digging in the literature, the recent literature, and we looked at the last 25 years or so of papers in RL. So you see this curve, it's actually growing very rapidly. Early 2000s, just a few hundred papers on the topic published every year. More recently, upwards of 20,000 papers being published on this topic. And so that's a lot of new findings coming out every year. And when we're asking what of all of these methods actually works in the real world, it makes it difficult to sift through all of that information. And so going back to the core topic for today, it becomes very important that the way the findings are reported in the papers match our criteria in terms of reliability, robustness, reproducibility. And so to check this out, we conducted our own little investigation, and we picked 4 papers. Out of the whole bunch of them, we picked 4, in particular 4 that were very well cited, commonly used, that was code available, and we started looking at how robust were the findings in those papers. And the message today that I'm going to deliver actually goes beyond those papers and is really looking at how we practice empirical science in this field. And so we started comparing some of these 4 different methods. These are policy gradient algorithms, different flavors of policy gradient, on this training of a very simple agent which learns how to walk. We call it the half cheetah domain, sort of a cheetah cartoon split in half, so only 2 legs. It has to learn to run without falling on its belly. And we compare 4 different algorithms. And on the left, you see a plot with those 4 algorithms. And on the basis of this, you would probably think that the red algorithm is doing quite a bit better than the other. It doesn't really matter which of the algorithms is which on this. Really, our message is about how do we do a fair comparison, draw conclusions that are robust from this. So based on this one, it seems this red algorithm is doing better. Now, we extended this to slightly different variations of controllers. There's another example, which is a hopper, and another one that's called a swimmer, slightly different versions of this character that we have to control. And when you look at the bottom 2 plots, what you see is actually the blue algorithm seems to be doing a lot better. And in the left bottom side, the blue algorithm is doing quite well with a really tight confidence interval, whereas on the right side, the blue algorithm is doing well, but with a really wide confidence interval. And so taking all these results together, you would think if you try the performance of each algorithm on more domains, you have a better understanding of how well it works and better prediction of whether it might be useful in the real world. And what we found here, we just got more and more confused with each of these experiments because the results just were not consistent from one to the other. We started digging in a little bit more about what might be going on behind the scenes. We thought, well, we didn't implement these algorithms on our own. Of course, we used some available open source code to do that. So we thought maybe we didn't get the right source for that. Maybe we got some poor implementation somewhere. We started digging out different implementations. And now what I'm showing you in the plot is 3 different implementations publicly available from one of these 4 algorithms called TRPO. And what you see here is one of these versions, the blue version, does a lot better than the other 2. We thought maybe TRPO is a policy gradient method that's a little bit unstable, code is hard to implement. We looked at some other cases, very similar results. You go from one code base to the other, it's purporting to be the same algorithm, it should work the same, right? And yet we're seeing really significant difference in the empirical performance. As we were asking more and more questions and diving deep into what might explain those differences, one thing we noticed is that in many cases, there's a lot of different hyperparameters that have to be configured. And depending how you set those, you get very different results. Most of the code bases come with a default set of hyperparameters, and it's very tempting to take that default set, not change it, and use it as is, out of the box. And what we found is once you start manipulating these different hyperparameters, it really changes the performance of your algorithm. So that's one lesson to take home. Really be very careful about what are the hyperparameters, how they're set, and how that might affect the performance of the algorithm once you run it on a new problem. You might be tempted to say, we're comparing different algorithms. The most fair way to do those comparisons is to give them the same amount of data, same amount of computation, everything's right. But from our analysis, as I've mentioned, what we've really found is that to draw robust conclusions, it's important to think a little bit more deeply about the issue. In particular, acknowledge the fact that different algorithms are going to have different hyperparameters. You can't just use the same from one to the other. The different methods are going to have different sensitivity to those hyperparameters. You might need to search longer and more carefully about some of them than others. And which method is best often depends on how much data you have and how much computation you can afford. And so that's going to change drastically from one application to the other, depending where your data is coming from and on what kind of platform you're trying to deploy your AI system. Taking all this together, stepping back to the main question, I think my main message for you today is that we have to be very careful about how we interpret the information that we read in papers, be very careful about how we set up our experiments, how we compare different methods, and when we do that, we can draw much more robust conclusions. And really, it goes back to the foundation of science. Science is an activity, a collective activity in which we engage, and the purpose of it is really to understand, to explain phenomenon. And to do that, you always have to be very careful about the way in which you're doing it. Thank you very much.
Congratulations! You finished your capstone project. By successfully completing each of the steps in the capstone, you should have been able to train an agent to land a module on the moon. And you should have some insight into how sensitive your agent is to one of its metaparameters. You already know a lot about the details of your solution and have seen learning curves and parameter sensitivity plots. So in this video, we're instead going to get some insight into the agent during learning. We'll visualize the agent in one run to get a sense of how an agent might learn on this problem. And of course, because it's fun to actually see our agent learn. This is a video of our agent after some training. You'll notice that the policy still isn't perfect, but it is quite good. But the agent definitely did not start there. Remember, it did not know anything about this world and had to learn by trial and error. Early on in training, the agent behaves in clearly suboptimal ways. For instance, perhaps the agent only decided to turn on one side thruster for the entire episode. That obviously didn't work out. After that, sometimes the agent learned to only use the bottom thruster. However, this pushed the agent far off screen, making it receive a large negative reward. If the agent can't use the main thruster all the time, and it can't use a side thruster all the time, obviously the correct choice is to just do nothing at all. We can try to hypothesize some reasons why this might be happening. One possibility is that the neural network is producing poor representations early on. For example, the agent might be overgeneralizing. If the side thruster action led to high negative reward in one state, the agent may overgeneralize that the side thruster action is terrible in all states. As the representation improves, the agent is better able to discriminate between states. Of course, this is just a hypothesis. Isolating the real cause will require some experimentation. After many more episodes of learning, the agent is performing much better. The agent is falling just a little too quickly, causing one of the corners to hit the ground. But fine-tuning its policy from here is relatively easy. And that's it for this video. It is fun to watch videos of your agent landing, but it can also be a useful way to debug and understand your agent. Whenever it's possible, it's worth taking the time to do this visualization to gain more understanding of your agent.
Congratulations! You have completed Course 4 and built a complete RL system. Let's quickly review the system you built. Throughout the capstone, we've been incrementally adding tools for solving the lunar lander problem. We started by formalizing the problem as an MVP and implementing the environment. This mainly involved precisely specifying a reward function to get the agent to appropriately land. We then discussed how to design an agent to learn a good policy in this environment. The first step was to figure out which reinforcement learning algorithms were appropriate for the given problem setting. We followed the course map that we built in Course 3 to narrow it down to 3 algorithms: expected SARSA, SARSA, and Q-learning. Next, we investigated how the choice of metaparameters influenced the agent's success. All the specific implementation details, including those about function approximation, exploration, and optimization, can be considered metaparameters. How we specify these can have a big impact on the performance of our agent. We discussed several of these choices and common rules of thumb. For example, we decided on the size and activation functions for the neural network based on conventional wisdom. However, some metaparameters, like the step size, can be difficult to select. This led to the final part of the project, a parameter study of the step size. Understanding our algorithms and systems is critical for successful deployment. Finally, you get to see your agent in action. We hope that you've learned a bit about the nuances of applying reinforcement learning methods in practice. There are a lot of choices to make, and it requires quite a lot of expertise and experience to get it right. Our goal was to give you some of that hands-on experience. Hopefully, this will help you in your future endeavors applying RL in the real world.
Congratulations! You've completed the reinforcement learning specialization.
We've come a long way since the first course, where you learned about the basic ideas of value functions, policies, and the sequential decision-making problem.
The easiest way to remember all that you've learned is to look again at our course map. We started in the tabular setting to allow you to get comfortable with many of the key concepts in RL without getting bogged down by the additional issues that arise when using function approximation.
We started by assuming you have a perfect model and focused on the key ideas in prediction and control. We talked about dynamic programming methods and how they solve Bellman equations.
We then moved to sample-based methods, where the agent is no longer given the model. It mainly learns from trial and error interaction with the world. We started by considering algorithms where the agent does not learn a model, including both Monte Carlo algorithms and temporal difference learning algorithms that use bootstrapping and so can learn and update their policy on every time step. These included Q-learning, SARSA, and expected SARSA for control, and TD for prediction.
We then revisited all these concepts using function approximation to learn approximate values and policies. We first talked about how Monte Carlo and TD algorithms extend to using function approximation. This required defining a loss function and understanding gradient-based approaches to optimization. We then discussed 2 new ideas, average reward and policy gradient methods. We learned about using average reward as a new way to formulate the agent's goal in continuing tests. We also learned how policy gradient methods can learn a policy directly by optimizing the average reward objective.
Our goal in this specialization was to give you foundational knowledge. Understanding the fundamentals is essential to using reinforcement learning appropriately. You hopefully now better understand when RL is well suited to a particular problem and how to formulate your problem as an RL problem. This seemingly simple thing represents a big step. Too often, people think, how can I apply the state-of-the-art in RL to my problem? When either a very simple approach is appropriate, or the problem wasn't even well posed as an RL problem in the first place. We want you to know better. Hopefully, you have learned something about being methodical and scientific in using RL. You now know how important it is to formalize your MDP or bandit, identify appropriate algorithms, and carefully evaluate and understand the performance of your autonomous learning system.
Knowing the fundamentals is the first step towards learning more about advanced topics in RL. What you have learned here will also help demystify algorithms you might read about in blog posts or scientific papers, ones that seem complex at first glance. You should now be able to see how state-of-the-art RL systems are actually built on relatively straightforward ideas. Never be impressed by things you don't understand.
My goal is to help more people understand and effectively use RL. I'm looking forward to seeing the things you accomplish with your new skills.
We have really enjoyed our time with you. It is so exciting to learn about a new topic for the first time. We also strongly believe that RL and AI will change the world for the better. You are now ready to play your part in that better world.